that? Okay. Great. So welcome back. My talk's going to be quite different from the one we just saw. We'll see if it is interesting. So when I first came in here, and this is also very loud. Okay. When I first came in and set up my network, the very first SSID I saw said DHS, and it reminded me of this funny cartoon. So I figured that might be a good thing for the topic. I'll have to remember that too when I go back home. So the title of my talk is very ambiguous. It's called Something About Middleware. But what I'm really going to talk about is patterns and frameworks for concurrent and network software. Now, this is something that I've been doing for a long time. I'm Doug Schmidt. I'm a professor at Vanderbilt University, where I've been for about a decade. And I've been teaching classes and writing books and papers, graduating students, and so on. But what I really like to do is I like to build systems, build software, and I like to work with people who build software. And so what I'm going to talk today about are some of the techniques I've found to be very effective for building software that has to take good advantage of the network and good advantage of the CPU, and nowadays, of course, the cores that we have at our disposal. This is motivated by 20 years of my work in this area on a lot of different projects. I've worked for a lot of work in aerospace and defense, done a lot of work in telco, written a lot of open source software. I'll talk a little bit more about that in a second. And one of the things I notice is when people start trying to build distributed systems or network systems that run across address spaces, there's a lot of complexity you have to wrestle with that you don't have to deal with when you're building more classic standalone systems. So when you build a classic standalone system, the latency is pretty low. It's predictable. If something fails, the whole thing fails. There's not a lot of partial failure. And the way you break your system up into pieces is largely driven by how much modularity you want. That's the main determining factor. When you start moving to building network systems and distributed systems, those characteristics are different. They're different challenges, different complexities. Latency typically becomes a big issue, trying to figure out how long it takes to go across the connection. Even on a high-speed network, the latency may still be a problem, especially if you're talking over a long, wide area network. Likewise, when something goes wrong, it's sometimes hard to figure out whether something's gone wrong or it's just slow. Things tend to fail in pieces. The whole system doesn't go down. Parts of it do. Back in the 90s, we used to have a saying where he said, a distributed system is a system where a file server you never heard of before causes your workstation to hang. Right? So that was what we thought of in those days. And it really was true. The file servers crashed an awful lot back in those days. And trying to sort that out is hard. Moreover, the way you break a system up into pieces is driven not just by the logical design constraints, but there's a lot of physical issues as well. Where do you run the processing? Do you have special purpose hardware where certain computations have to run? And so on and so forth. So there's a lot of things that become much more difficult in that space. Fortunately, there are common solutions to these challenging topics. And if that wasn't the case, then nothing about what I'm about to say would make any sense. The hard part about this is to figure out how to capture these common solutions in a way that everybody can learn from and apply to what they're doing. And so that it becomes somewhat less of a black art, somewhat less of a black hole to pour resources in when people go out and try to build networked and concurrent solutions. So there's a couple of things we're going to talk about today. One of the key topics is the topic of a pattern, and the other topic is the topic of a framework, and I'll give you lots and lots of examples of these things to try to make it a little bit more clear. So a pattern is basically a solution to a problem that arises in a particular context. We're obviously going to talk about building software, but patterns apply lots of other places as well. If anybody here has ever driven through New Jersey, you've probably noticed something there they call the jug handle or the J-turn or jug handle pattern. And it's just pervasive. Everywhere you go in New Jersey, there are these crazy jug handle-like things. And it's worth asking the question, how did this end up this way? Why does New Jersey have so many jug handles? And the reason, of course, why they have them is because New Jersey is one of the original states, one of the original colonies. It's very densely populated. I think it's the most densely populated state in the country. And the infrastructure has grown organically over a long period of time. And what that meant was that things used to be footpaths, became horse paths, became two-lane horse paths, and then maybe buggy paths, and then someone paved them. And that's where a lot of the roads came from. And because it's so densely populated, there's businesses and homes right up next to the roads everywhere you go. So as a consequence, if you want to make a left-hand turn in New Jersey, you've got this big problem. And the problem is something that network queuing people and routing people, I'm a routing guy, as the guy said before, would be very familiar with, which is something called head-of-line blocking. So if you're trying to make a left-hand turn in New Jersey, you've got a problem because if there's oncoming traffic, you're going to have a bunch of people queuing up behind you, and there's a big jam. Now, if this was California, where they built the road systems much later, and they could have, giant superhighways with 6 lanes on each side, totally full of traffic, by the way, but they at least had the infrastructure in place, you would make a left turn lane to solve the problem. In New Jersey, because of the cost of the infrastructure, they can't do that. So what they do instead is they build what's called a jug handle. Sometimes they're called J-turns. And they buy some land. They make a right-hand turn that lets you go left. They put a 7-Eleven or something here, or a gas station. And that's a pattern for resolving forces that are very characteristic of New Jersey civil transportation infrastructure. When we go to build software, there are also many forces that constrain us. We don't always think about them in quite as of a tangible way as people trying to build road systems, where the forces are pretty obvious, but they're there nonetheless. And so there's often forces that lead us in certain directions. We may want to leverage some existing code, so we have to work with the installed base. We may have to make something real small or real fast if we're trying to build a deeply embedded system. We may want to be able to leverage our investment by building something that's reusable. And these are things that influence the way that we build the software. And experts at building software learn to work with these forces. They learn to take these constraints and use them to shape their designs. And when they go to build the next system, they don't start from scratch. They don't start from first principles. They bring along all those collected patterns that they've learned over time. So patterns are basically described in terms of roles and responsibilities and the way that the software interacts with different pieces in a manner that leads to a desirable result. So just to give you a very, very simple example of a pattern that occurs a lot in distributed systems, there's something that's called the proxy pattern. And if you're building a system that has to run across address spaces, whether they be across address spaces on the same machine, like a co-located server on a Linux machine, or some processes that are running separately on an Android device, or if they're running across a real network, you have two choices as a developer. One choice is to write a lot of low-level code yourself using abstractions like sockets or some kind of local inter-process communication mechanism, in which case the application developers have to become familiar with how to deal with encoding and decoding and byte order and marshalling and demarshalling and demultiplexing and all that kind of good stuff. Or, more likely these days, you apply what's called the proxy pattern, where you develop some kind of component or service or object that sits between the client application and the server and does all that heavy lifting and the dirty, grubby work of transforming between the different address spaces automatically. So that's a classic example of a very simple pattern that helps make life somewhat easier for people building distributed systems. Now, about 20 years ago, people started to really think carefully about how to design software and to document and capture that knowledge. And there was a book that came out at the time called the Design Patterns Catalog by the so-called Gang of Four. And it's kind of the original book on software patterns. And back in those days, people were doing a lot of work with user interfaces, maybe some data access kinds of things. The people doing patterns weren't really doing networking or concurrency and so on. And if you read that book, you'll learn a lot of good classic patterns, but you won't really learn how to write patterns that work effectively if you're trying to solve these other more modern problems, like how do you program for a multi-core machine, or how do you take advantage of a high-speed interconnect. So over the last 20 years, a lot more stuff has come along, and there's now quite a variety of literature to talk about these patterns for all kinds of other things besides just user interfaces. So I'm going to be focusing on some of the interesting patterns that arise when you build concurrent and network systems. As it turns out, however, the patterns just get you part of the way there. Patterns are great, as we'll see in a second, because they make it possible for people to learn a common vocabulary. It allows teams of software developers to communicate with each other in a more intuitive and meaningful way. It allows people to avoid a common problem we run into in software teams where people tend to get wedded to the programming language they use, which is important, but what's really important in the long run, especially for bigger, more complex systems, are the design techniques you apply. And patterns let us focus on design without getting wrapped up in the implementation details at the right point. So they're really valuable. However, patterns don't write the code. So patterns make you smarter, patterns make you more effective, patterns make you more fun at parties with your friends. Oh, okay, maybe not. But they don't write the code. So we need something else. And that something else, which we'll also talk about a little bit, is something called frameworks. Frameworks are basically integrated sets of components or objects or functions or services, whatever your unit of abstraction is, that collaborate to provide a reusable architecture for a family of related applications. So there's a couple key things there. Some things that have well-defined interfaces and boundaries that work together that provide a reusable architecture that can be applied to various domains. And patterns or frameworks are characterized by three key things. One of the most important things is something called inversion of control, which means that it calls you back as opposed to you calling it. You may call it originally, the framework, to register some callbacks, but after that, it's driven by events that come back to you. This is sometimes humorously referred to as the Hollywood principle, which says, don't call us, we'll call you. So that's what that's one of the characteristics of a framework. And think about classic things. If you've done much programming, you're probably familiar with class libraries or function libraries and so on. Those don't really have inversion of control. You own the event loop. You own the control flow. You direct where things go. Frameworks invert that. The second thing that frameworks do is they provide support for domain-specific functionality, structures and functionality. And that's why what you typically see in framework applications are things that are either kind of computer science geeky domains, cool stuff like user interfaces or networking or databases, or more application-centric domains like the domain of e-commerce or avionics mission computing or scientific visualization. It's things where you're not just reusing objects, you're reusing control flow as well. Common interaction patterns are also covered in the framework. And the third thing a framework provides is basically a semi-complete application. If you've ever done any development with toolkits like Android or user interface toolkits, you know that the amount of code that you actually have to write is relatively small, and an awful lot of the stuff you get comes to you from the framework. This semester, I'm teaching a course that some of you are taking on Android systems programming. And we're just having a blast getting in there and playing around with the systems programming features in Android. And there's lots of cool framework stuff there, services, content providers, and so on. There's also tons of GUI stuff as well, so activities and so on. And it's amazing how little code you need to write to build very powerful applications really quickly. So those are some of the things that make frameworks useful. I'm not just talking about this in the abstract. I've developed frameworks over a long time. Back when I was a grad student in California about 20 years ago, I started to develop a set of frameworks for concurrent and networked applications written in C++. I was doing a lot of Unix network programming back in those days, and it was a lot of fun. I was a great fan of the classic Richard Stevens books on Unix network programming, but boy, it was painful. And we'll talk a tiny bit about some of the pain when we talk more about the patterns. And I was also at the same time really learning about object-oriented design and C++ and other higher level yet still very efficient abstractions. And it was surprising to me how most people building software in those days that were concurrent and networked were relegated to using very low-level techniques, which meant that they couldn't avail themselves of all the powerful abstractions that were coming along in other ways. So I developed something called ACE, which is a very widely used open source framework for doing various concurrent and network kinds of things. And it's been ported to many, many different systems, including a lot of real-time systems used in lots and lots and lots of real-world applications. And it gives me a different insight about how this stuff really applies. What's interesting about ACE, when all is said and done, though, is not the several 100,000 lines of C++ code. It's the underlying design abstractions. That's the part that's most valuable. And I discovered that the hard way. If you are a technologist long enough in our field, whatever it is you started with, whether it was, in my case, Pascal or Ada, way back in the 80s, C++, C later, and so on, if you wait long enough, that stuff's going to go away, unless you're a COBOL programmer, in which case it's called job security, right? There's so few people left doing COBOL that it's a great way to make a lot of money and a good way to pay for retirement. But the reality is that things are going to shift a lot out from underneath you. So whatever your language du jour that's your popular approach, it's going to change over time. But what's most interesting to me is the fact that the underlying patterns, the design abstractions, the way you put the pieces together, those things change much, much slower. And once you master the patterns, then the languages can change, the operating systems can change, the middleware can change, and so on. But you still have valuable knowledge because you understand how to solve the problem in a more effective way than somebody who just knows the latest tool, latest technique. So what patterns allow us to do, and what I was able to do with the middleware I developed, was document the ways in which the different patterns work together to carry out larger parts of the design exploration and design space. So we use them to preserve knowledge. If you've ever built a lot of software, especially if you built software that you've worked on over many years and maybe you kind of went away from for a while and have come back to, it's always amazing how quickly you forget why you did what you did. A lot of the open source software I built started back in the late 80s, and there's still people who are using it today. Some of the software I developed back in the 89 time frame found its way into the GNU distribution. I wrote a perfect hash function generator program called gperf, which is still part of GNU. And people still write me and say, you know, how does this work, or how did you do this? And to be honest, I go back and I look at that crappy code I wrote, 25 years ago, and I'm like, I didn't know what the hell I was doing. And that's not unusual, right? And even if you get better at it, you find yourself continually forgetting what you did. So what patterns help us to do, as we'll see in a second, is they help provide us with concepts that are easier to understand than the low-level code to guide us through the design. And they're especially useful if you're trying to learn somebody else's code. When we work with Android, technologies that were developed from the mid-90s onwards have a tendency to be very pattern-oriented. So Java, C#, very, very pattern-oriented. If you're a C++ developer, things like the STL, the standard template library, very, very pattern-oriented. And when you learn those things, if you're looking at the code for Android or other stuff that's come later, it's just a joy to look at, even though the code may be complex, because the patterns provide a structure to learning how the pieces fit together. So we're going to look at some of these patterns, and I'll give you some concrete examples. So rather than just talking about patterns in the abstract, I'm going to try to give them some real life by talking about something that's kind of fun to develop, and that's a high-performance web server. So this is something we all use, probably all take for granted at this point, but somebody had to sit down and build this thing originally. And when I was at Washington University as a professor back in the 90s, we were interested in trying to see if we could build high-performance servers using a pattern-oriented approach. And so the goal was to make them both very flexible and easy to understand and very portable, while at the same time also making them as efficient as we could. And that trade-off is something that the right knowledge of the right patterns can do very effectively. I'm not going to bore you with what a web server does. You all know what it does. You send various GET requests, and those things travel over TCP/IP. They're encapsulated in a very thin transfer protocol called HTTP, and that is just depending on which version it is, a very, very thin layer on top of TCP. And then, of course, there's a whole pile of things on the GUI side that send requests and parse the responses and so on. But the server side is where we're going to focus. So on the server side, you typically have three basic architectural abstractions in a web server. By the way, this applies for almost any server that deals with stuff from the outside world. You have an event dispatcher that gets the input from the network. You've got some kind of protocol handlers that do the processing for HTTP, 1.0, 1.1, other kinds of protocols you might have. And then there's some kind of super-duper file cache to try to speed the way you look up commonly accessed content. Those are the three main things you have. Now, what do you want to do with this stuff? Well, you probably want to make it robust. You want to make it so if somebody comes along and connects to your server and then never bothers to send you a GET request, it doesn't leak resources for very long. So you want to make it robust to sort of obvious kinds of attacks. You might also want to make it extensible. Once you build a server that works well, you can use it for lots of stuff, not just HTTP, as we'll see in a second. And you may also, of course, want to be able to leverage the latest and greatest in the hardware we have available to us. So you want to be able to take advantage of multi-core. You probably want to be able to take advantage of all the cool operating system support that's now in most modern operating systems to do high-performance web transfers, things like the transmit file capabilities in Windows, or some of the cool file transfer stuff that you have, send file capabilities you have in Linux, and so on. So how to do this? Well, first let's look a little bit more in the architecture, and then we'll see how patterns are going to help us out. So if you were to try to take this design and go talk to your designers, people building systems, and I'm just focusing on web stuff because it's an easy place to start, but people building software do the same kind of thing no matter what it is they do. They get together as a group, as a team, they talk about what the requirements are, people bring forth their favorite approach, and then we debate as engineers. We love to question, we love to interrogate each other and push each other and challenge each other to come up with better solutions. So if you were to offer to people, these are the abstractions that you need to have, right away, first of all, there would be all kinds of disagreement about whether this is the right way to break things up. And the second thing is you'd have to figure out how to handle many sources of variability. That's the thing that makes software hard. Software is pretty easy, except for the fact that things keep changing, right? Requirements change, users have different needs. the environment changes. We move it from Windows to Linux. We were talking earlier about Solaris. It's kind of gone away, but many of the abstractions live on. We move to embedded systems. And so how do you account for all this variability? Some of the variability that you would deal with if you were to try to build a high-performance web server or a high-performance server would be the following. Variability in concurrency model. Do you use a thread pool? Do you use a thread per connection, thread per request? These kinds of things make a big difference in terms of latency, in terms of scalability, in terms of memory utilization, and so on. There's also variability in terms of event demultiplexing. If you're on a Unix-like platform, you'll probably use a select-like mechanism or a poll-like mechanism. If you're on a Windows platform, you'll probably use something else. Windows is very asynchronous in the way it treats its demultiplexing. There's different caching models, there's different content delivery protocols, and of course there's the never-ending specter of different portability constraints as we move between Windows versus Unix, or the 17 different versions of Linux, all of which are slightly different. These are issues we have to deal with that account for variability. So how are we going to make the world a better place through patterns? Well, one of the first things we're going to be able to do is we're going to be able to do more than just draw a picture of our architecture. And if you have experience working in a team, you know the minute you make something concrete, people start to say, well, wait a second, how about this way, how about that way? And what we're going to use is we're going to use a set of patterns to help justify and rationalize why the architecture looks the way it does. And this is a very, very powerful technique. It can be abused. People who understand patterns in a very superficial way can impress their peers and convince them to go design choices that are probably incorrect. So you have to have expertise. But by the same token, it helps people think very explicitly and rationally about how they design their systems. Now again, I'm focusing on the web stuff just because that happens to be something I like to think about. But you can imagine many other aspects of trying to be in an organization. There are patterns for analysis if you're doing analysis for user needs. There are patterns for doing appropriate vulnerability inspection analysis. There's patterns for all kinds of other things besides this. This is just one little case study to illustrate the point. And what these patterns allow us to do is they allow us to address a whole bunch of challenges at the design level that would otherwise make things more expensive, make things more hard-coded, make things harder to change. And those kinds of things make a big difference for a lot of reasons. If things are harder to change, then when your customers come along with some new requirements, it takes you a lot more time and costs them a lot more money they may or may not be able to afford to make things evolve. Now, if you're getting paid by the hour, not a bad deal. If you're trying to reduce your costs by building a product that can be easily retargeted and extended to new platforms and new requirements, it's a big deal. So there's a pile of things we're going to talk about. I'm not going to read through this list because I'm going to give you some concrete examples of how we can actually use this stuff in practice. So here are some of the ways that we can apply patterns to resolve certain challenges when we build concurrent and network software. So one of the issues you deal with, whenever you're building a server, invariably it's got to talk to multiple clients. So you've got to have this issue of simultaneous access to your server by more than one thing at a time. So how do you do that? Well, first of all, how do you do that? And also, what do you have to do? One of the key things you need to be able to do is called demultiplexing, or multiplexing, depends on your point of view, whether you're looking at it from the top or the bottom. And basically, this is about trying to keep track of who has sent you what information so that after you're done processing the request, you make sure it goes back to the appropriate client who sent it in the first place. So how do you do this? Well, if this was 1995, we would use select. And oddly enough, people still tend to use select. Select is a Unix systems programming abstraction. It's a function widely ported to VxWorks and Windows and most other platforms, which is why it's so widely used. And what it does is it lets a single thread of control wait for stuff to happen from multiple sources of input. And if you ever take a look at code written using select, and it's probably hard to see this, but it's ugly anyway, it typically looks like this. You set up a set of handles for things you want to listen for events on, like connection events and so on. You call select, you block, you wait for select to return. When select returns, it tells you what things have happened. And then you typically have some kind of loop or a bunch of low-level code that checks these bit masks that come back from select, figure out what happened, and then do stuff. You accept connections, you read and write data, and so on and so forth. And inevitably, when people program software like this, they have a tendency to tightly couple the event demultiplexing logic, the select part, with the protocol processing logic, the part that's reading and writing the data, with the actual application logic that's doing the real business logic. And if you ever take a look at the code that people write, and I go all the way back to the absolute Bibles in our field, the Richard Stevens books on Unix network programming and the Steve Rago book and stuff, you look at that code, it's very, very tightly coupled. And that's a problem, because the minute you want to change anything, everything breaks. I worked for a company in the early 90s in Silicon Valley that was doing online transaction processing, and we were using sockets and select. And for some God knows why reason, at that time, Sun came out and said, thou shalt move away from sockets and select and move towards this weird thing called TLI, which was the transport layer interface, and POL. And we'd written all of our code to use sockets and select. And we went through there and we gutted it and we used if-defs and just made a big mess. And it never quite worked right because there were just little tiny variations. And that taught me an important lesson. If you program to the raw, low-level APIs, you're screwed when anything changes. And that lesson has come back over and over throughout my career. So what we want to be able to do is come up with a better solution, something that's more scalable, more stable. So one way to do this is to apply something called the reactor pattern. Now, anybody who's ever programmed with X Windows, if anybody remembers X Windows use the reactor pattern very heavily. If you program with more modern, object-oriented frameworks, they use this pattern very heavily. And basically the idea here is you have an abstraction, which is called the reactor, strangely enough. And what it does is it abstracts away from the low-level ways in which you get events into your system. So you might have an abstraction that works with select, but you can also easily plug and play the various poll operations that we have, epoll, kernel KQ, all these other crazy things that keep coming along that are really cool and much faster, dev poll, wait for multiple objects, all the things that you get on the different platforms. And those can be abstracted away and hidden, so your application code never sees that. Likewise, we can also go ahead and develop this reactor, which is basically a container that holds a bunch of event handle tuples. The handle being a file descriptor or a socket or whatnot, where events can occur. And the event handlers being some kind of callback thing. If we're in object-oriented land, it's a base class. If we're in C world, it's a C function, etc. And the cool part about this is application developers can now focus on the event handlers that do the application logic, and we can push all the low-level gobbledygook into the framework that implements the pattern. So things are hidden, which is good. Now, one of the classic critiques you get when you tell people about this, especially systems programmers, they go, well, that sounds really good, and abstraction is sort of mumble, but it's going to be slow. Well, and so the good news is, once you build an abstraction layer, you can then spend time optimizing the heck out of that abstraction layer. And just to give you a couple of simple examples of this, I built the first reactor implementation back in the early 90s. And it did what people did in those days. It looked through a list of FD sets, which are little bit masks, and looped through them one at a time. And it was easy to write, but it was incredibly inefficient. And if you had 1,000 bits that might be set, it would loop for 1,000 times, even though only 1 or 2 bits was set. Really slow. Well, because we were doing open source, we released this, and people liked it. And then some crazy guy in Colombia, South America, discovered some really cool algorithm that could look at a set of bits and determine which bits were set in that set in time proportionate to the number of set bits, not the number of bits in the set. So if you had 1,000 bits, but only 2 were set, it would only take a couple of loops to get all the bits that you needed to extract. So he went in and he changed, 15 lines of code in our abstraction, and all of a sudden, everybody who used the reactor was way faster. And everybody who used select written by hand using a for loop was way slow. So that taught me another important lesson about patterns and about abstraction. If you do it right, you can actually optimize things way beyond what you could do by hand because you're able to affect change through very narrow interfaces. So a good lesson about performance and optimization. The way these patterns actually play out in practice, you register event handlers in an initialization phase, and when you're done, you turn the control over to the framework, and at that point, everything is driven by callbacks. So this is the inversion of control principle we talked about before. So as things happen, callbacks occur, cool stuff takes place, your application code gets called, and you don't have to know or care about what's going on under the hood. So Reactor, very, very common pattern. A pattern that's used very frequently with the Reactor pattern is a pattern called the Acceptor Connector pattern. Acceptor Connector is a real easy pattern to explain with a couple of human known uses. So if you're an important person in an organization, you don't take your own phone calls. Somebody else takes them for you. So when I want to call the dean or the chairman, I call the number and it's his receptionist who answers. So there's this notion of an acceptor or a receptionist that accepts the connection, and then if you're important enough to get through to the right party, you get to talk to a real person, and then you have a conversation with that person. So this notion of an acceptor role is something we all know from everyday life. If you're an even more important person in an organization, you don't make your own phone calls. So when the dean wants to call me, he doesn't call me. His receptionist calls me. I'm like, oh, come on. And so basically, if I was important enough, I'd have my own acceptor, right, to accept the call, but I'm not that important. So his receptionist calls me, but there's this notion of a connector and an acceptor, and those are kind of routine positions, jobs, capabilities that are fairly straightforward to do, and so you can imagine making a reusable abstraction for them. And what really matters is getting the service handlers initialized to do the real work. And so the Acceptor Connector pattern is basically a pattern that describes how you break up your system into an event processing layer, like a reactor. It doesn't have to be a reactor, but it could be a reactor. And then an Acceptor Connector layer that does the connection handling, both actively and passively. And then the things that actually do the real work. So armed with these abstractions, it gets really easy to build sort of foolproof network systems because you're not programming at the socket level. You're not sitting there going, gosh, do I have a listen mode handle? Can I call read and write on this thing? Oh, my type system is really primitive because it's basically dealing with untyped pointers or ints. So these abstractions build you a little wall to hide yourself from complexity and mistakes. So armed with this couple of patterns, Reactor and Acceptor Connector, we can now start to build a very simple web server that you can put together almost in no time at all, especially if you have a framework that implements these patterns. So the patterns give you the design, the framework gives you the code. So we could develop things so we would have an HTTP acceptor and an HTTP handler. This would be the only code that would be anywhere specific to our web server, and everything else gets inherited and reused and managed by abstractions that we got from someplace else, either from a design point of view or an implementation point of view. Here's a little picture that shows how this all works, just to illustrate this, and this will become important when we start talking about concurrency, because you'll see how we can start adding concurrency to the solution to make it more scalable without breaking the architecture, which is another really key benefit of a pattern-oriented view. The architecture comes first, and then the implementation follows from that. By the way, I should mention that you have to have a lot of implementation expertise to get to the point where you can have your architecture drive things, that the architecture doesn't just fall off the turnip truck. So in this model, you register your acceptor with a reactor, and when a client connects, that does a callback to the acceptor, which creates a handler, which itself registers itself back to the reactor. And then when data actually shows up, then the reactor calls back to the handler. It opens up the file, or it looks in a cache, however that's done, and then it sends that data back to the client. Okay, so far so good. You can build a functional web server using Acceptor Connector and Reactor in pretty much no time flat if you have a framework that implements that stuff. But there's some problems, right? One of the big problems you're going to run into very quickly is scalability. Obviously, there's two issues. Number one, if you have a fast server talking to a slow client, and the server is single-threaded, and the network connection pipe gets full, won't get into the details of how that works, but TCP has a window flow control mechanism that says to the sender, hey, stop sending, you're talking too fast, I can't keep up. You're going to cause your server to block, which is a bad thing. It means you're massively underutilizing your capabilities. And of course, when you start having hundreds of thousands of clients, it makes no sense to have one thread, right? So that's not going to scale. So what can we do to make things effective? Well, once again, patterns to the rescue. So it turns out there's a couple of different ways to solve this problem using pattern-oriented approach. And without getting wrapped up in the details, I want to give you more the design perspective. So you're an architect, you're a designer, you're trying to build a high-performance system, you've got things, basic functionality working, you try to run it in practice, it doesn't scale. What do you do? Well, what you historically would do is you go back and start rewriting all the code again at great expense. A better way to do it is to build things on the right pattern architecture so that when things don't scale, you go back into your repertoire of patterns and figure out other patterns to combine that gives you the requirements you need without changing much of what you've done. So in this particular case, one thing we can do is we can apply a really cool concurrency pattern called the half-sync, half-async pattern. Now, anybody here who's got background in operating systems, especially more traditional operating systems like the BSD Unix family, you remember back in the day, you had a kernel that was not multi-threaded, it was interrupt-driven, and then you had user-level abstractions that were multi-processed, right? A process was the abstraction you had in those days. And if you look carefully at the way that those kernels were constructed, or those systems were constructed, the OS never blocked. It was asynchronous, driven by callbacks. And then you had application processes that could afford to block. Well, that was a pattern, and it was done that way for a very particular set of reasons. It was much more efficient to implement the kernel with interrupts, but for God's sake, most people can't program like that. The kernel programmers can. Dennis Ritchie can program that. Nobody else can. Bill Joy can program that. But then at the application level, they wanted to have simpler abstractions. But you don't want to make the threading or process-based abstraction be in the kernel because it's too slow. So they came up with an architecture that gave you the best of both worlds. It was asynchronous at the bottom, synchronous on top. So we can leverage this particular set of patterns to solve our concurrency problem for our web server. And what we can do is we can apply, as we'll see in a second, threads in the sync layer which talk to a async layer through a queue. Now, again, if this was an operating system kernel, this would be the kernel, this would be the socket layer, these would be the processes. But the pattern applies at the user level as well. So what we can do in this case is we can apply these to threads, and by applying to threads, those could be mapped to cores. And of course, even if they're not mapped to cores, the semantics of modern thread libraries allow an individual thread to block without causing the whole server to hang. So it allows us to be able to scale things up in quite a number of interesting ways. So the way this pattern works, you have some external event occur, like an incoming request, and that, through some kind of interrupt or other non-blocking mechanism, informs the async service layer. It does some amount of work, but doesn't block, plops the request into a queue, and then goes back to waiting for the next round of things to be done. And then at some point, the synchronous layer is notified that there's work for it in the queue. It wakes up and grabs the event out of the queue and processes it. Those are the dynamics. So we can apply this pattern to our web server to make it multi-threaded quite easily. In fact, we can leverage all the stuff we already had there. So what we could do is we could do the connection establishment part using a reactor and an acceptor. And then once you've read in the HTTP request, you could stick it into a message, stick the message on a queue, and then have a pool of threads sitting around in what's called hungry puppy fashion, waiting for requests to come from the queue. And one of those threads would get to pull the message out and do the processing. So without changing much in our design, we're now able to scale up much more effectively. That begs another question, of course. How do you write that request queue? So once again, patterns to the rescue. If you think about the request queue, it's got to be able to allow a thread in the pool to wait when there's no work. And it's also got to allow something in the bottom, the async layer, to block potentially if the queue is full when it tries to put something in there. That's a trickier issue. Probably want to just drop messages in that case. But you certainly want to have people be able to wait on the queue when there's nothing for them to do. So how do you do that? Well, of course, the silly, naive thing to do would be to sit there with no locks whatsoever and just read data out of a queue. And that would have all kinds of race conditions and scheduling hazards. A less naive, but still silly thing to do would be to have a busy wait that just sits there looping on some kind of mutex, checking to see if there's any work. That's also silly as well. The right thing to do is to apply a pattern called the monitor object pattern. Now, back in the day, to understand this pattern, you had to go out and read some esoteric concurrency literature by people with funny names from the UK, like Hoare and stuff like that, and basically try to figure out what a monitor was. Nowadays, it's easy. It's built into languages like Java and C#. But even if you're not programming in Java and C#, you could still apply the pattern in C++ or C. And basically the way this pattern works is it allows you to define the method call as the concurrency boundary. And the way it works is that you have this thing called a monitor object with synchronized methods, and when a client or clients invoke calls on the method, only one method at a time is allowed access into the object. And that is enforced by something called a monitor lock, which is basically a mutex, or mutual exclusion abstraction. If it turns out, for whatever reason, that you can't get all your work done without blocking, you can use something called a condition, or a monitor condition, to put yourself to sleep and let somebody else do the work. So by using these abstractions, you can use objects as a unit of concurrency. You can protect access by the monitor lock, and you can schedule the interactions between threads by using conditions. And I'm not going to bore you to death by explaining this diagram in great detail, but it's really cool how this works. And once you kind of get it, it's really, really easy to build concurrent applications that use objects as the way of communicating. So we can go back here, and we can use the monitor object to implement synchronized request queue. And then when stuff comes up from the reactive layer, it gets plopped into the queue, and then one of the threads in the layer up here, the concurrency layer, goes ahead and pulls things off the queue. Another way to look at that, by the way, yet another good example of the power of patterns, is we can end up with what's called an active object pattern on top of a reactor pattern. So one way to implement half sync, half async is with active objects and reactors. I won't go into detail about that right now, but the key point there is that patterns often work best when they're composed together to form longer sequences of patterns. So just to take a step back, what I've shown you so far is by using a sequence of patterns in combination, reactor, acceptor connector, half sync, half async, monitor object, and so on, we can start to put together a scalable and efficient web server or server without having to think too hard about it. The design issues really kind of program themselves, especially if you have the code that does this. Well, this works pretty well, and a lot of web servers are built like this, a very, very, very common technique people use, but it's not necessarily the most optimized way to do things. Sometimes that matters, sometimes it doesn't. So it turns out that a more optimized way of doing a web server, especially a web server that's trying to implement the HTTP 1.0 version of web processing, is by using some cool optimization that's built into all modern operating systems now. And this is called the accept optimization. And what you can do on Solaris, Linux, Windows, you name it, these days, couldn't do it 10 years ago, but now you can do it, is you can have a group of threads all calling accept on the same passive mode or listener mode socket handle. And whichever one gets there first gets the next socket that's been connected from a client. And so this is basically pushing the queuing down into the kernel, and it's allowing the performance to be really, really fast. So if you want to write a really fast HTTP 1.0 server, this is probably the right way to do it. So that works great. The problem, however, is that that's not always feasible for various reasons. For example, if you're implementing an HTTP 1.1 server where a connection is kept open for a sequence of events, that optimization doesn't really help you anymore, because a connection and a request are not one and the same. There's also some other problems with the half-sync, half-async-like approach, and it really has to do with the overhead of concurrency. Now, if you're a Java programmer, you probably don't think about this stuff. One of the funny things I find about Java is it tends to encourage people to pretend like performance overheads don't exist. And so as a result, you spawn memory like there's no tomorrow, you spawn threads like there's no tomorrow, it's really easy, and it's not until you realize just how incredibly slow your applications are that you wonder, I wonder if that was such a good idea. But the good news is we don't have to do that. But here are some of the consequences of not thinking about some of these issues. So half-sync, half-async is very scalable, but there still are some things that make it less efficient than we might want, especially for short requests. Here are some of the problems. When you start doing this stuff, when you start moving requests between threads, that pretty much necessitates the use of dynamic memory allocation. And when you start doing that, there's a cost to it, and there's a locking overhead to it as well. So there's locks you have to acquire. Moreover, when you start moving things between requests, you have to start grabbing locks to synchronize them between threads. That has a cost as well. The big hitters, though, are context switching, which occurs when you have to stop one set of things and then restart something else in a different context. That's a big hitter. And then there's also the issue you run into in multi-core machines with moving data between caches. So it may turn out that even though this solution will scale, the latency will be reasonably high because of these overheads from concurrency. Can we do better? Well, of course we can do better. How do we decide what to do better? We apply the right set of patterns. So there's another pattern. This will be the last pattern I'll talk about, and then I'll wrap up. Something called the leader-followers pattern. This pattern is really easy to explain for anybody who's ever spent time going through airports and trying to get a taxi cab. If you go to most airports, they have a very simple protocol which implements the leader-followers pattern, where you have a line of people waiting for cabs and a line of cabs waiting to service people. And the rule is the next person at the front of the line gets in the next cab at the front of the line, and away they go. And this works because, at least in theory, at most airports, any cab can take any person any place. So you just sort of self-organize. There are some airports, by the way, where that is not the case. If you go to Washington National Reagan National Airport in D.C., for some strange reason, different cabs can only go to different places. So they have cabs that go to D.C., cabs that go to Virginia, cabs that go to Maryland. And they have a person standing there basically coordinating where you go. So when you get to the front of the line, you may actually have to wait because the cab for you isn't there yet, for where you're trying to go. That's a more complicated queuing model. But leader-followers works great if everybody is equal, if every thread / cab can take every event / person where it needs to go. And so basically what you do is you can spawn a pool of threads that take turns waiting for the next event to come. And when you do this, what you can do is, unlike the half-sync, half-async approach, the thread that receives the request is the same thread that processes it, which means that the context switching, data movement, and synchronization costs and the need for dynamic memory allocation are greatly reduced. So it's actually much more predictable, much more low latency. The downside with this particular approach is it doesn't scale as well. So basically, this is like adding a thread pool to a reactor. And I won't go through all the different variants and all the different issues. But the key thing about this is, once you understand this pattern, if you're building a real-time system, if you're building a system where latency is important, if you're dealing in a system where predictability is important, more important than scale, then the leader-followers concurrency approach may be for you. Conversely, if you're building a system where scalability is more important than latency and predictability, the half-sync, half-async approach is right for you. The key point about this is that we can have a nice discussion about optimizing the performance of systems without having to talk about whether we're using C++, C, or Java, without having to talk about the implementation details of one data structure versus another. We can talk about it from the point of patterns and architecture, which means we can have a very informed discussion with people who don't have to know all the details all the time, come up with the right solution that fits the needs, and then go and implement it most efficiently. So it turns out that you could apply this and it would work very well for certain scenarios. I've used the leader-followers approach a lot when I build real-time embedded systems where the latency and predictability are crucial. Even though the performance is great, there's still some reasons why you might go to use the other pattern, the half-sync, half-async approach. One reason might be that with half-sync, half-async, because there's a separate queue, you could reorder the events, so you can have the events show up in a different order than the order of arrival. It's very hard to do that with leader-followers. Another reason is you can end up doing the queuing for half-sync, half-async in virtual memory, which is typically vast these days, whereas with leader-followers, the queuing is typically done in the operating system kernel, of which there's not much memory. There's 100K or so per connection. So the point here is that neither one is right or wrong. It's about trade-offs. It's about forces. It's about thinking about the design. So to kind of wrap up and leave you with a couple of thoughts, in my experience, when you start trying to build complex systems that have to live for long periods of time and involve groups of people who need to figure out how to keep track of all the details over time, patterns are invaluable for getting the teams to have a more common view of things. And once you have a team that starts to learn the vocabulary, you can be much more effective in design reviews, code inspections, bull sessions about trying to figure out what you're doing. But that's not enough. You've got to go further. So frameworks provide you with the implementation of these patterns. Most frameworks these days are off the shelf. If you're a Java programmer, you are a consumer of a vast number of frameworks, or an Android programmer, lots and lots of stuff. If you're an ACE user, lots of stuff out there. And middleware, since this was nominally something about middleware is basically the codification of patterns and frameworks within a standard set of interfaces that are going to kind of shave off some of the sharp edges of the frameworks. Frameworks give you tremendous power, but they're somewhat complicated to learn and build. So middleware is what really makes it easier to use. And the great thing is nowadays there's tremendous feedback going on here. The reason I mentioned Java before as a great example of pattern-oriented solutions is because Java was really being developed around the time that patterns were really spinning off, mid-90s. So all the people who did Java and Java class libraries and Java virtual machines and Java frameworks were using the patterns. And so you'll see, decorator, observer, proxy, all over the place in those technologies. And some of the stuff that we have done over time with the patterns that we've worked on have also found their way into those systems. So other stuff, if you're interested in this kind of technology, I've written a whole pile of books, and there's also lots of stuff on my website at Vanderbilt that will give you pointers to papers and source code and lots of other stuff in this space, much of which is being very widely used. And most exciting, perhaps for me at least, is Vanderbilt, in about 2 months ago, has decided to enter into the MOOC dimension. MOOC is a massively open online course. And there's an organization called Coursera, which has been formulated. People probably know about Coursera, Udacity, Khan Academy, edX, and so on. These are different groups that are doing MOOCs in various flavors. And Vanderbilt's a part of the MOOC wave, and I was selected to be one of the first 5 professors at Vanderbilt to give a course on Coursera. And it's, well, you can't quite see it. If you go to my website, you'll see it. It's called Pattern-Oriented Software Architectures for Concurrent and Network Software. And it's going to start in about 3 months, February 4th. It'll be 6 hours long, or six weeks long, about 2 hours a week, all through the web. You can watch the videos. There'll be little pop-up quizzes and assignments that you can follow along with. And so something cool has happened. So I've been teaching courses now for about 20 years, maybe 50 students a year, so that's about 1,000 students over 20 years. It's been about 6 weeks since they announced this. I have 12,000 people signed up so far. So I would have to teach, I'd have to teach students for 1,000 years at Vanderbilt to teach that many students. And I bet by the time the course actually starts, it'll probably be more like 30 to 50,000 students. So that's unbelievable, right? The amount of people you can reach and the way you can teach them is just phenomenal. So it's going to be a lot of fun. We're going to try a whole bunch of new techniques with automated grading of programming assignments and other kinds of things, which should be kind of an interesting experiment from the point of view of how do you secure your network, right? You don't want people hacking in there. And it also gives us a chance to rethink the way we teach courses at Vanderbilt, because we're going to use all this material when we do the face-to-face courses to help make the students more involved and more interactive. So I encourage you to take a look. If you have any questions, feel free to drop me a line. I'll be happy to tell you more about that. Yes, sir. Yeah. Yeah.
Why wouldn't I use something like 0 and Q? Or what's the difference or the trade-off between 0 and Q? I mean, because the way I understood you were talking about Acceptor is using Acceptor as a queuing process, right? It's not quite that.
So what I would describe there was an incredibly low-level hack, right? So what you do there is the kernel, the operating system kernel, manages a queue of pending connections that have been completed and are ready to be accepted, right? And so you can have a pool of threads in the application all calling accept on the passive mode handle. And accept, as I'm sure you know, is a factory that returns to you a new connected handle, right? New connected socket descriptor. And so what you do is each thread in the pool calls accept all at the same time, and the queue gives each of the different threads a different connected socket. And then they go ahead and do read and write. So they kind of morph from being an acceptor thread to being a read-write thread. Well, the queue, you're right, absolutely right. The queuing, not the queue, the queuing is done in the kernel at the socket layer. So the half-sync, half-async thing, which I think was maybe where you're headed with this, that's building a queue, a real queue, a user-level queue, middleware-level queue, on top of the kernel-level queues. Because, of course, sockets are queues, of course, but they're kind of out of your control, and they're very small, which is why you have flow control. And so you can build your own queue on top of that, where you could make that as big as the virtual memory you wanted to allocate. And of course, middleware, all the middleware that layers on top of this stuff uses that somewhere down in the bowels of the middleware. Well, I mean, the minute you start, a lot of these scripting languages started out being used for fairly small things, and then as people started to use them for more ambitious things, they had to evolve, right? Because otherwise you'd spend all your time writing infrastructure and missing the point of the productivity boost. And we see that with Android and all the other frameworks like that as well. Any other questions or comments? Yeah. I'll be happy to send the slides or leave them. I can put them on a thumb disk. But you can set. Yeah, let me put this back up here. So just send me email, and I'll send you the slides. Actually, if you go to my website, which is also up there, you will find more slides than you could possibly ever absorb in a million years. And the Coursera course that I'm doing will also cover this stuff. And the great part, you can either speed it up or slow it down, right? So if it went by too fast, you can slow it down if I go. Yeah. Yeah, it's a fun topic, and it's obviously at the core. It's not security per se, but it's the infrastructure that we need to secure the systems to make them work. Mike.
So, for people out there that are interested, they want a resource, a book, or 2 books.
Well, if you want to know about patterns, you're probably a good starting point. Just patterns, qua patterns, would be this book here, the Design Patterns book, the so-called Gang of Four book, because there were 4 authors. I was in Beijing, China, many years ago, and I was giving a talk about patterns, and I kept talking about the Gang of Four and how great they were, and I love the Gang of Four, and these guys were like, "Is this guy nuts?" You know. So there's a context issue that's important. So that's the starting point for patterns. The POSA books, of which I was co-author of 3 of 5, are also good. If you're more interested in concurrency and networking, those are good. If you're really into Java concurrency, then I highly recommend the book by Doug Lee called Concurrent Programming in Java, which is just chock full of cool little patterns for programming in Java concurrency. And a lot of the stuff in his book has found its way into Android and the various abstractions they have, like loopers and all these other things. And just to make the whole thing really cool, people, now that these things have become codified, there are automated design checker tools out there, like SureLogic, where you can actually check your code, your Java code especially, to see if it's violating design rules of concurrent software. And so it's just a great example of how patterns find their way into languages, find their way into tools to check whether you use them correctly. So if you're an Android developer or a Java developer, this SureLogic tool is just fantastic to catch a gazillion bugs. It's kind of like Lint on steroids for Java and Android programmers. So very cool stuff. Yeah, but feel free to take a look. Any of those books are good. My website has lots of stuff. It's kind of a portal into that world. And if you have any questions, just let me know. I'll be happy to help you. And hopefully you'll join Coursera, and we can see each other virtually. Thanks, guys.